You're standing in a kitchen with a wooden floor, hardwood planks, evenly spaced. You drop a needle, just a regular sewing needle. It lands on the floor, and now you've got a question. What's the probability it lands on a line between the planks? You'd think the answer would be something simple, right? 50-50, heads or tails logic. But the universe is not that generous. The probability, it turns out, is exactly 2pi. Beat pi. That irrational, infinite decimal that has absolutely nothing to do with lines and gaps. Pi, which is supposed to be about circles, about circumferences and diameters. It shows up in the probability of a needle falling on a wooden floor. This is Buffon's needle, a problem posed in 1733 by a French mathematician named Georges-Louis Leclerc, Comte de Buffon. Not a physicist, not an experimentalist, a pure theorist with a pen. And he figured out that if you drop needles on a striped floor, the ratio of successful landings to total drops converges on pi. Beat. You can actually calculate pi by throwing sewing needles. This is not a metaphor. This is not an analogy. This is literally how the ancient mathematician John Venn estimated pi in the 1600s, and it was accurate to several decimal places. And it's not the only time math decides to show up in places it has no business being. Welcome to the Existence Experiment. I'm Travis R. Barlow. Today's episode, The Constant. Why is pi everywhere? Why is the universe speaking mathematics? And if math is everywhere, does that tell us something fundamental about what reality actually is? In 1960, physicist Eugene Wigner wrote an essay with a title that still makes physicists slightly uncomfortable: The Unreasonable Effectiveness of Mathematics in the Natural Sciences. The whole point was, why does this work? We invent these abstract systems, these formal languages of numbers and symbols, rules divorced from any physical reality, and then we point them at the real world, and they predict what's going to happen. They predict it absurdly well. We use Maxwell's equations, which are mathematically elegant abstractions describing how electric and magnetic fields propagate through space, and we can calculate exactly where light will bend, how fast it travels, why the sky is blue. We use general relativity, which is fundamentally a description of the curvature of spacetime expressed in tensor calculus, and we can predict gravitational waves. We literally heard those in 2015, colliding neutron stars, billions of light years away, and we had the math to predict the exact frequencies in the signal. This should not work. Think about it. We didn't discover these equations in nature. We invented them. We sat down with pen and paper and we said, let's describe waves with this differential equation. Let's describe probability with this distribution. Let's describe motion with these force laws. And then, mysteriously, when we test these inventions against reality, they work. Sometimes they work so perfectly that physicists get uncomfortable. We call it unreasonable. It's as if we're speaking the universe's native language without ever being taught it. The hard question underneath is simple. Are we discovering something that's already there, or are we just very good at pattern matching? If math is invented, if it's a human language, a tool like English or JavaScript, then it's wild but not mysterious that it matches reality. We invented it to match reality. We shaped it through centuries of feedback. But if math is discovered, if the equations are already embedded in the fabric of the universe waiting for us to find them, then something much stranger is going on. Then mathematics might be fundamental. Then math might be the source code. And here's what makes this question so sharp. In previous episodes, back in episode 5 where we talked about the universe as source code, and episode 7 where we examined the nature of time, we kept coming back to the same paradox. If the universe runs on mathematics, what is mathematics running on? What's underneath? What's the base layer? Is there an infinite regress? Or do we stop at mathematics and say this is foundational? This is the floor. And if it's the floor, then mathematical constants are not just descriptive, they're ontological. They're part of what it means to exist. Let's talk about pi specifically, because it's the most famous constant and it's the most egregious offender. Pi is defined as the ratio of a circle's circumference to its diameter. That's it, circles. Nice, bounded geometric objects that exist in Euclidean space. Pi equals 3.141592653588979. Repeating forever, non-repeating. A truly irrational number, not rational, not expressible as a ratio of integers. It's one of the infinite constants that makes the real numbers infinite in a way that integers never can be. We've computed pi to trillions of digits and no pattern has ever emerged. It's as random as white noise, mathematically speaking. But here's where it gets weird. If you flip a coin a huge number of times and ask, what's the probability distribution of heads in a certain window? You get the normal distribution, the bell curve, the Gaussian distribution. And that normal distribution, the famous equation with the exponential bell shape, its formula contains pi, explicitly, in the denominator in the normalizing constant. Why? The coin doesn't know about circles. The coin doesn't know about geometry. The probability of heads on a fair coin is unrelated to circles. Yet pi emerges from pure probability, from counting. From the moment you ask the universe to distribute a large number of random events, pi shows up to organize them. River deltas. You know rivers? They wind. They curve back on themselves. They don't take straight paths down hills, they meander. Geomorphologists noticed something remarkable. The ratio of the actual length of a river to the straight line distance from source to mouth, that ratio on average across most rivers on Earth, averages to approximately pi. A beta. Rivers flowing downhill under gravity, creating sinuous paths, eroding banks, depositing sediment, all of this governed by fluid dynamics and friction and channel geometry, and the average sinuosity constant is pi. Pi again. Not from design, not from circles, just from the physics of flowing water interacting with landscape. The Mississippi River has a sinuosity of about 314. The Amazon similar. Patterns repeat across climates and continents. Then there's quantum mechanics. The probability amplitude for a particle behaves like a wave. It literally requires pi in the mathematics of wave functions. Schrodinger's equation, the fundamental equation of quantum mechanics, has pi baked in. The wave function psi evolves according to an equation where every term is decorated with factors of pi or 2 pi. And pi shows up in the radiation formulas, in the quantization rules, and the uncertainty principle itself. Heisenberg's uncertainty principle says that the product of position uncertainty and momentum uncertainty is at least h bar divided by 2, where h bar is Planck's constant divided by 2pi. B. 2 pi. The reduced Planck constant is defined with 2p in the denominator. Why? Because the relationship between waves and particles in quantum mechanics is intrinsically linked to pi. Wavelength, frequency, the de Broglie relation, all pi. Even in the quantum realm, the one place we most expected math to break down and reality to do something weird and non-mathematical, pi is there, holding the mathematics together, mediating between the wave and particle descriptions. And then there's Fourier analysis, the mathematical technique that converts time domain signals into frequency domain representations. Audio files, radio waves, the electromagnetic spectrum. All of these rely on Fourier transforms, and the Fourier transform is built on sine and cosine functions, which are built on circles, which are built on, you guessed it, PA. Every time you stream music, every time a cell tower routes your signal, every time a doctor does an MRI scan, pi is there in the mathematical machinery. Pi has become synonymous with the decomposition of signals into periodic components. You cannot separate pi from periodicity. Pi is not alone. There's another constant that shows up everywhere, and it's called phi, the golden ratio. Approximately 1.618033988. Another irrational number, another infinite decimal with no pattern. It's defined as the solution to a specific equation. If you divide a line such that the whole is to the large part as the large part is to the small part, that ratio is phi. It's an elegant self-similar definition, a ratio that contains itself. Mathematically, it's the solution to x squared minus x minus 1 equals 0, which gives you 1 plus the square root of 5 divided by 2. It emerges from geometry, but it's also a number, a constant, a universal pattern. And where does phi appear? Spiraling shells, nautilus shells, create logarithmic spirals that grow at phi's rate. A spiral where each turn is phi times larger than the last. The arrangement of leaves on a stem, the phyllotaxis, often follows Fibonacci patterns, which in the limit converge on phi. The branching of blood vessels, the proportions of the human face, debated but recurring, the ratio of consecutive segments in your fingers, the spiral of a galaxy. Phi appears again and again in living systems. The Fibonacci sequence 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, each term is the sum of the previous two. And the ratio of consecutive Fibonacci numbers approaches phi in the limit. This is not coincidence. This is how growth works when you start with self-referential rules. Nature loves phi because phi is what emerges when you grow according to simple recursive rules. Every living thing is built from recursive rules. Therefore, every living thing loves phi. Then there's E, Euler's number, 2.718281828459004. Another irrational transcendental constant. Unlike pi, which comes from geometry, E comes from growth. And E shows up whenever you're describing continuous natural growth or decay. Compound interest follows E. If you invest money and let it compound continuously, the growth follows E. Radioactive decay follows E. The number of atoms remaining follows E to the negative power of time. Population dynamics in ecology, bacterial growth, the cooling of coffee according to Newton's law of cooling, the charging of capacitors, the discharge of a capacitor, the shape of a hanging chain, the catenary, all E. The number that represents continuous natural growth. It's the base of the natural logarithm, and it's so fundamental that mathematicians consider it one of the five most important constants in existence. Here's why E is fundamental. It emerges from asking a simple question. If you have a quantity that grows proportional to itself, meaning the more you have, the faster it grows, what's the growth function? The answer is e to the power of t. It's inevitable. It's the unique solution. And the universe is full of self-reinforcing systems. More atoms means more decay products means, wait, that's decay, the negative version. More people means more births means more growth. More heat difference means more cooling means, again, the negative. The point is that anytime a system's behavior is proportional to its current state, E appears. This is ubiquitous. E is not about circles or geometry. E is about the mathematics of change itself. And here's Euler's identity, one of the most beautiful equations in mathematics. E to the power of I times pi plus 1 equals 0. Beat. Five of the most important constants in mathematics connected by a single equation. E, the growth constant. I, the imaginary unit. Pi, the circle constant. 1, unity. And 0, nothing. All connected. The equation is so elegant that physicists print it on t-shirts. It's the most beautiful equation ever written, and it appears to be true in the structure of reality itself. Why should an exponential growth function, an imaginary unit that represents rotations in complex space, and a circle constant combine to produce nothing? What are the odds? Everything we've discovered suggests those odds are very high indeed. Now, I want to talk about a constant that genuinely unsettles physicists. The fine structure constant, usually written as alpha, equals approximately 1 divided by 137.0036. Beat. That 137 is not an accident. It's one of the great unsolved mysteries of physics. Richard Feynman, one of the greatest physicists of the 20th century, looked at this number and said, "It is a magic number that comes to us with no understanding by man." You might say the hand of God wrote that number and we don't know how he pushed his pencil. Beat. This is Feynman. Not prone to mysticism, but confronted with 137, he couldn't help himself. The number haunted him. The fine structure constant describes the strength of the electromagnetic force. It determines how strongly light and charged particles interact. It's dimensionless, which means it doesn't depend on what units you choose. Whether you measure in meters or inches, kilograms or stones, whether you use SI or Planck units, the fine structure constant is always 1 down 137. We're very close to it. The precision measurement is 1137.03599.084. 39 decimal places of precision. And physics has no explanation for why. We can't derive it. We can't predict it. We measure it, and then we plug the measured value into our equations, and the equations work. But we don't know what 137 is doing there, or why it chose that particular value out of all the possible values it could have chosen. Wolfgang Pauli, one of the greatest physicists of the 20th century, spent decades trying to derive why alpha equals 137. He became obsessed with it. He corresponded with Jung, the psychologist, about the symbolic meaning of the number. He couldn't solve it. When he died, he left behind notebooks filled with attempted derivations, each one failing. The number refused to yield. Physicists have been trying ever since, for over 100 years now, and the mystery remains unsolved. Some have speculated that if alpha were even slightly different, say 136 or 138, chemistry would be impossible. The fine structure splitting of energy levels in atoms would change. Atomic shells would reorganize. Stars might not form. Elements might not exist. Life, as we know it, couldn't exist. We live in a narrow band where alpha permits chemistry, permits complexity, permits us. It's a Goldilocks number. The fine structure constant sits at the intersection of three deep physics mysteries: quantum mechanics, electromagnetism, and relativity. The fact that it has this precise value, that we can't derive it from first principles, that Feynman couldn't even approximate it, this is a hint that we're missing something foundational. Maybe alpha is not a constant at all, but a parameter. Beat. A hard-coded value. A tuning knob set at a very specific position. What if you could zoom out far enough to see the interface? What if there's a parameter adjustment screen somewhere in the layer below physics, and 137.036 is the current setting? That's wild speculation, but it's the kind of wild speculation that keeps physicists up at night. And here's what's even more unsettling. Some physicists have proposed that alpha might not actually be constant. What if it's changing with time? What if it was different in the early universe? Some cosmological observations have hinted at this, though the measurements are controversial and difficult. But imagine if true. Imagine if the fundamental strength of electromagnetism has been slowly drifting since the Big Bang. That's not a constant, that's a variable. And if it's a variable, what's causing it to vary? What's the underlying mechanism? We don't know. We've never known. 137 remains the magic number. Here's the philosophical crux, and it matters for everything. Beat. When Newton discovered his laws of motion, did he invent them or discover them? When Maxwell sat down and wrote his equations describing electromagnetism, were those equations already true before he wrote them down, or did he create them? This is not just academic navel-gazing. The answer determines whether mathematics is a language or a reality, whether constants are invented symbols or genuine properties of the universe. There are basically three camps in modern philosophy of mathematics. The nominalists, and they include many working scientists, pragmatists who don't care about metaphysics, say that mathematics is a human invention. We create these abstract systems because they help us describe patterns in nature. Pi doesn't actually exist in the universe. Pi is a concept we invented to describe the ratio of a circle's circumference to its diameter. The number 137 doesn't mean anything fundamentally. It's just what we get when we do the calculation to determine electromagnetic interaction strength. Mathematics is a useful language. A tool, nothing more. Useful fictions. This view is practical, economical, and it lets you sleep at night. But then there are the Platonists, and they say something radical. Mathematical objects exist independently of human minds. Numbers are real, equations are real. They live in some abstract realm, Plato's realm of forms, some people call it, or the Platonic heavens. And when we do mathematics, we're not inventing anything. We're exploring, we're discovering truths that exist timelessly, spacelessly, beyond the physical universe. When you prove a theorem, you're not creating something new. You're uncovering something that was always true. The theorem was true before you were born, before humans existed, before Earth formed. It was true in a realm of abstract objects that exists outside of space-time. The Platonist view is deeply weird, and yet it keeps winning in the hearts of mathematicians. Because how else do you explain that mathematical truths about things humans never knew about still turn out to be true? Non-Euclidean geometry was developed as pure abstraction. Mathematicians like Gauss and Lobachevsky created alternative geometries where parallel lines behave differently, where the angles of a triangle don't add up to 180 degrees. For decades, these geometries were considered philosophical fiction, interesting but useless. Then Albert Einstein showed that space-time itself is non-Euclidean. The geometry that was invented in the mind turned out to be the geometry that the universe actually uses. Beat. Mathematicians had discovered something true about the universe before the universe revealed it. How is that not discovering? How is that inventing? And there's a third view, growing in influence, formalism. Formalism says that mathematics is neither discovered nor invented. It's a game played with symbols according to arbitrary rules. A number is just a symbol. An equation is a sequence of symbols manipulated according to formal rules. Mathematics is complete, consistent, and meaningless. It's pure syntax, and the fact that the syntax matches reality might just be a lucky accident, or it might reveal something deep about how syntax and reality are related at the most fundamental level. Which brings us to the physicist Max Tegmark's hypothesis, the mathematical universe hypothesis. B. Tegmark proposes something radical. The universe is not merely described by mathematics. The universe is mathematics. The physical universe is a mathematical structure. All of the properties we perceive, matter, energy, space-time, the constants, are mathematical properties. We're not using math as a language to describe reality. Reality is made of math. The map and the territory have collapsed into one. And if that's true, then every constant, pi, e, phi, alpha, are not arbitrary features of a separate reality. They are the structure itself. They're bedrock. They're the atoms of mathematics. And mathematics is the only thing that exists. The mathematical universe hypothesis sounds insane, but it's actually parsimonious. It says there is one thing, mathematics. Everything else is a subset. No need to explain why math fits reality so well. Reality is math. No need to explain where mathematical truths come from. They don't come from anywhere, they just are. The universe exists not because some external cause made it exist, but because it's mathematically possible to exist. And we exist as subsystems of that mathematical structure, which is why we can know mathematical truths. We're made of the same substance as the truths we're discovering. Before we close, let me play devil's advocate. All of this, the Platonism, the mathematical universe hypothesis, the idea that constants are the source code, maybe it's beautiful thinking that requires no evidence. Maybe the reason PI shows up everywhere is mundane. Maybe we live in a universe governed by certain physical laws, and those laws are expressed in mathematics because that's the only language we have that's precise enough to describe them. The universe isn't made of pi. The universe just behaves in ways that, when translated into human mathematics, involve pi. We invented pi. Humans sat down and said, the ratio of circumference to diameter is an interesting quantity. Let's call it pi. Then, when we looked at nature, we found that nature obeys differential equations, and when we solve those equations, pi shows up. But that doesn't mean pi is fundamental. It means the physical laws are fundamental, and pi is a consequence of how those laws interact with the geometry of circles and waves and spirals. The appearance of pi is not evidence of the reality of mathematical objects. It's evidence that we chose a mathematical language that naturally encodes circular geometry. Rivers wind because water follows gradients. It takes the path of least resistance. And the mathematics of how water flows under gravity, combined with sediment deposition and erosion, naturally produces sinuous curves. The sinuosity ratio being pi is not evidence that pi is the universe's favorite number. It's not evidence that pi is fundamental. It's evidence that sinuous curves with those statistics have a natural mathematical description in which pi appears. We're pattern matching. We created a system of symbols, mathematics, and we got very good at matching it to patterns. That's not the same as the universe being made of mathematics. That's just showing that we're good at metaphor. The fine structure constant might be 137, not because it's a fundamental parameter, not because it's hard-coded into the source code, but because of how quantum mechanics and relativity work together in the deep mathematics of quantum electrodynamics. And when we compute the value, we get that number. It's not magic. It's derived. We just can't derive it yet from principles more basic. The physicist can't see the derivation, but that's only because our theories aren't deep enough. Ask any working physicist. Would you rather have discovered that alpha is fundamental and inexplicable, or would you rather hope that someday a theory more foundational than quantum electrodynamics will derive alpha from first principles? Every single physicist would choose the latter. They'd rather math be invented and derived from something deeper than leave it standing alone as a mystery. They'd rather pull back the curtain. And here's the kicker. Maybe the Platonists are right that mathematical objects exist, but wrong about where they exist. Maybe mathematical objects exist only in the brains of thinking creatures. Maybe they're features of conscious systems that evolved to model reality. In that case, mathematics is discovered. It's discovered in the structure of physics, but also invented. It's invented by brains. It's both. The two activities converge in the act of learning mathematics. So where does that leave us? Is the universe mathematical? Is mathematics discovered or invented? I don't know. Honestly, after a decade of thinking about these questions, after interviewing physicists and mathematicians and philosophers, I'm not sure the distinction is even meaningful. If we invent a language that maps perfectly onto reality, and if our brains are made of reality, then the language is part of reality. The invention is made of the invented. The finger pointing at the moon becomes another part of the moon. The menu and the meal have merged. But I'll tell you what's interesting. We live in a universe where constants emerge, where patterns repeat, where mathematical structures show up in places they shouldn't, where a sewing needle and a wooden floor can teach us about circles, where five fundamental constants lock together in an equation so beautiful it looks like poetry, where a mysterious number, 137, shows up in the strength of light itself and our best physicists can only shrug. That demands explanation. Either the universe is made of mathematics or we are, or the distinction has collapsed into meaninglessness. Those are your three options, and none of them are comfortable. Next time on the existence experiment, we move from the noise of mathematics to the sound of silence. We're going to talk about Fermi and his paradox. Why, if the universe is so vast and so old, do we hear nothing? Where is everybody? We're going to explore the possibilities that terrify us most. The silence might be telling us something, and it might be the most honest thing anything has ever said. The existence experiment is written and hosted by me, Travis R. Barlow. If this episode made you uncomfortable, that's by design. Think about it. Share it. Let it sit in your mind like a prime number, irreducible, strange, and somehow speaking to everything. And if you have a constant you think I missed, an equation that changed your life, a place where math showed up where it shouldn't, email me. I read everything. I'm still trying to understand 137.